To increase the capacity of a deep learning model, you normally have to pay for it in computation. A larger model requires more hardware, drawing more power every time it processes an input. This animation shows why. In a standard dense neural network, the parameter count and the per-example floating point operations are strictly coupled. An input vector must pass through every single node in the matrix to generate an output. If you scale this dense matrix up by a factor of 1,000, the math breaks down. Executing every node for a single forward pass creates a compute load that modern hardware cannot physically sustain. In 2017, a team at Google Brain led by Shazeer published a paper targeting exactly this bottleneck. Their objective was to achieve greater than a 1,000x improvement in model capacity with almost no increase in computational cost. The mechanism they used to do this is called conditional computation. Instead of forcing every input through the entire network, the architecture activates highly specific, isolated parts of the network on a strictly per-example basis. By ensuring most of the network sits idle during any single forward pass, conditional computation acts as the architectural lever that decouples a model's total capacity from its per-token compute cost. The paper executes this concept by introducing the Sparsely-Gated Mixture-of-Experts, or MoE layer. In their language modeling experiments, this acts as a drop-in component inserted directly between stacked LSTM layers. The layer's internal structure consists of independent feed-forward networks, the experts, alongside a trainable gating network. When an input arrives, the gate produces a sparse vector. This actively blocks data to the majority of the network, leaving only K experts active. The mathematical output of this layer is the gate-weighted sum of those active experts' outputs. Wherever the gate outputs a 0, the corresponding expert is completely skipped. No parameters are loaded into memory, and no floating point operations are performed. Skipping inactive blocks allows the network to absorb hundreds of billions of parameters in total capacity without paying the computational penalty during the forward pass. To understand how the model routes these inputs, we have to look at the internal mathematics of the gating network to see how it decides which K experts to activate. Here are the raw logit scores for all N experts, calculated via linear projection. The gate adds tunable Gaussian noise from a second matrix, dynamically shifting the scores. Then truncation keeps only the top K values, like K equals 4, setting all others to -infinity. The gate applies a softmax function to the remaining values. Because the truncated values were set to -infinity, the softmax forces them to exactly 0, creating a mathematically true sparse vector. The injected Gaussian noise in this equation is not a standard regularization technique. The noise is a functional requirement designed to smooth out the discrete binary boundary of whether a score makes it into the top K threshold. Because the paper routes inputs to multiple experts, maintaining K greater than 1, the top K gate values preserve real non-zero gradients. Combining the Gaussian noise with a K greater than 1 routing configuration allows the entire sparse gate to be trained end-to-end via standard backpropagation. The architecture completely bypasses the need for complex reinforcement learning algorithms like reinforce. Left to its own devices, sparse gating encounters a fatal hardware flaw: routing collapse. The routing mechanism creates a self-reinforcing loop. Favored experts train slightly faster and produce better outputs, causing the gate to select them even more frequently. The remaining experts sit idle, wasting the model's theoretical capacity. To prevent this collapse, the authors added an auxiliary loss to the overall task loss. The first constraint, the importance loss, explicitly penalizes any uneven distribution of gate weights across a batch. But balancing the gate weight alone is insufficient. An expert could receive 3 examples with massive weights, while another receives 30 examples with tiny weights. Total importance may be equal, but computational workloads are lopsided. To fix this, they introduced a second constraint, the load loss. Leveraging probabilities from the Gaussian noise, this loss balances the actual number of discrete examples routed to each expert. This requires a specific initialization trick. The gate and noise matrices must be initialized to all zeros. This yields no routing signal and forces a roughly even load distribution before the soft constraints have time to warm up. If gate weights were initialized randomly, initial imbalances would flood specific experts with data, immediately triggering an out-of-memory error across the GPU cluster. Together, these two soft, differentiable constraints force the network to distribute its data cleanly, ensuring the 1000x capacity increase is actually utilized rather than ignored. Theoretical mathematics only work if the hardware can execute them. Naively deployed, sparse routing actively starves a GPU cluster. This animation illustrates the shrinking batch problem. If a gate routes K out of N experts for a batch of B examples, each expert mathematically only receives a tiny variable fraction of the batch. As you see here, the compute efficiency gauge drops entirely. GPUs require large, uniform batch sizes for matrix multiplication to amortize parameter loading overhead. To fix the shrinking batch, they overlap two paradigms. Standard layers are replicated across devices via data parallelism, while experts are model parallel shards, one shared copy per device. By running these replicas synchronously, each device gathers all the tokens assigned to its local expert from across the entire cluster. This step restores the per-expert batch size by a factor of the total number of devices. The authors applied two secondary fixes to push batch sizes even further, exploiting convolutionality by batching all time steps simultaneously and recomputing hidden activations on the backward pass to save memory. Algorithmic sparsity is useless without a rigorous, hardware-aware distributed topology to maintain matrix multiplication efficiency on the physical chips. To see how far this hybrid parallel architecture can actually scale, we can look at the paper's experiments on the Google 100 billion word corpus. At extreme scales, a standard flat gate becomes impractical. The architecture requires a two-level hierarchical MoE. A primary gating network routes to a cluster of secondary MoEs, which then use their own gates to select the final leaf experts. Even when spanning tens of thousands of options, the hierarchy routes inputs so that exactly 4 leaf experts are executed per token. The architecture demonstrated its peak empirical success when scaled to 65,536 experts, containing roughly 68 billion parameters. At this scale, it yielded a 39% improvement in perplexity over a compute-matched dense baseline. But the architecture has a breaking point. When the researchers pushed the configuration to 131,072 experts, roughly 137 billion parameters, perplexity degraded. The authors hypothesize this degradation stems from too much sparsity, as activating 4 out of 131,000 options creates a 99.994% layer sparsity. This extreme division was compounded by a sharp collapse in physical GPU floating point efficiency. Scaling parameters via conditional computation hits a hard limit, where the integrity of mathematical routing intersects with the physical constraints of hardware efficiency. For engineers familiar with modern iterations of this concept, like the 2021 switch transformers, the original 2017 architecture operates on entirely different routing mechanics. Switch transformers hardened the gate to a top 1 argmax and introduced static expert capacity limits and drop token rules. The 2017 architecture operates entirely on soft, continuous weighted combinations of multiple experts, without hard token dropping constraints. This sparsely gated conditional computation was the primary lever that allowed parameter count to finally diverge from per-example operations. By combining differentiable Gaussian gating with a hybrid distributed data parallelism, this paper defined the precise engineering foundation required to build the modern era of massive parameter models.